This video will introduce the concepts of work and energy. We will define work as the scalar product of the force and displacement. We will use the equation work is equal to force times displacement times the cosine of theta to determine the work done. And we will use force displacement diagrams to calculate the work done by a variable force. And just to introduce and give you an overview of the topic, the concept of work and energy provides a powerful means of understanding a range of processes. So we're going to be able to use it to solve a number of problems involving situations where energy is changing. When work is done on an object, energy will be transferred to the object. There are different forms of energy, and energy can be transferred from one object to another, but it cannot be created or destroyed. So firstly, the concept of work. So if we push or pull something and make it move in the direction of the push or pull, then we will do work on the object. The amount of work done is determined by the product of the component of the force in the direction of motion and the displacement of the object. And the final answers that we get will be measured in Newton meters, i.e. force times distance, or joules, which has the symbol capital J. Okay, so let's have a look at this situation here. We have a man pulling a box, and the force is being applied at an angle. The displacement of the box will be along the horizontal plane, so it's only the horizontal component of this force that is going to do work on it. So let's have a look at this video, if it will let me click on it. Let's just see here what's going on. There we go. So he pulls it. The work done is the force times the distance, which will be the force times the displacement times cosine of theta. So our final equation for work is this, and we're going to apply this to a number of situations. Okay, so here's an example. We pull a trolley along on a string, which applies a tension force of 50 newtons at an angle of 30 degrees to the horizontal. The object moves a distance of 2 meters. So like that. How much work is done by the force? So here we say work is equal to force times displacement times the cosine of the angle. So this is going to take into account the fact that the force is not in exactly the same direction as the displacement. So that is going to be equal to 50 times 2 times the cosine of 30, which is equal to 50 times 2 times 30 cosine, which gives us 86.6 joules. Except we were given information to two significant figures, so that's 87 joules. Okay, so that's a simple application of this work equation that we've just introduced. Work can sometimes be done against the motion. So if we do work against the motion of an object, then we'll apply a force in the opposite direction to displacement, and that will result in negative work being done. So often friction is the force that does negative work on objects that are sliding, because it acts in the opposite direction to the motion. So if we think of this situation where we have a box which moves along a surface and friction is acting against the motion and it moves 2 meters, oops, let's just go back to that. Then the work done, the work done is equal to the force applied times the displacement, and in this case the force and displacement are along the same plane, so we don't need an angle here. Or we could put the angle as times cosine of 0, and cosine of 0 is 1. So here we have negative 50, which is the force. We're going to use the convention that to the left is negative and to the right is positive, times positive 2. So that's equal to negative 100 joules of work. So in this case, the work that's being done on the object is negative. In other words, that work is going to cause the object to lose energy. Okay, so if we push a crate along the floor by applying a horizontal 100 Newton force so that it moves a distance of 1.5 meters at a constant speed. So here we are applying, so we have a box. We are applying a 100 Newton force, and it's going to move a distance of 1.5 meters. How much work did we do on the crate? Well, the work is just equal to force times distance times cosine of theta, but theta here is 0. So that is equal to 100 times 1.5, this is 1, which is 150 joules. It was moving at a constant speed, so we know, so this is the this is F push. If it's moving at a constant speed, that means that there must be an equal and opposite force acting on it because it's in equilibrium. So we have a friction force acting here in this direction of 100 newtons as well. And so the work done by friction is going to be equal to negative 100 times 1.5, which is negative 150 joules. And therefore we see that the total work done on the box is 0. Friction why is this not working? Here we go. So 3, friction will convert the energy, the work that we've done, to heat or thermal energy. So delta E is equal to 150 newtons, sorry, 150 joules, and that will be equal to the thermal energy gained. So that will basically all the energy that all the work that we did is converted by friction to heat in the surface between the floor and the bottom surface of the crate. Okay, so a convenient way of looking at work is to draw a force displacement graph where the force is the component of the force in the direction of motion. So we can then find the work done by calculating the area, sorry, that should say area under the graph line. So here we have an area here. So the work done is equal to 50 times 2, which is 100 joules. 100 joules, yeah. So this seems a bit unnecessary for a constant force, but you can see that it's true, that basically the area is going to be the force applied times the displacement in the direction of the force. This becomes particularly useful when we're looking at variable forces, however. So if you look at this diagram, in this situation we have a force being applied of 100 newtons, and then the force gradually drops to 0 over the last 10 meters of displacement. And so here we can find finding the work done with the equation would be tricky because the force is changing over the last part of the motion, but we can use the force displacement diagram to find the force quite easily. So work done is equal to area under graph, And so the work done here is equal to 100 times 20, which is this area here, area 1. Area 2 is going to be a half times 100 times 10, because this distance here is 10. So the total work done is going to be equal to 200 plus a half of, sorry, 2000 plus a half of 1000, which is 500. So that's 2500 joules. Okay, so this is a convenient way of representing forces acting on objects in order to find the work done. And we'll use this later on when we're looking at the work done by a spring. So we're now going to use the work energy equivalence to derive equations for gravitational potential energy, and we're going to use the work energy equivalence to derive equation for kinetic energy, that Ek equals half mv squared, and both of those equations should be familiar to you, but you may not have seen how they can be derived. So the work energy equivalence says that when we do work on an object, the object's energy will change by exactly the same amount as the work done on it. The amount of work done on the object is equivalent to the energy change of the object. This is the principle of work energy equivalence. We can use this to define types of energy. So this idea of work energy equivalence, I should just note, kind of ties together the concept of energy with the concept of force. And so this ties in our energy discussion to our earlier discussion of Newton's laws. So let's look at gravitational potential energy. When we lift an object, we have to apply an upwards force equal to the object's weight force. So we're going to be lifting it at constant speed here. The work done in changing the object's height by delta H can be determined. So if we look here at this box, if we move it upwards a distance delta H, then the energy that it gains due to the work that we've done against the gravitational force will be equal to the gravitational potential energy. So we can figure that out here. So the force that we apply is equal to mg. The displacement over which we've applied that force to the object is equal to delta H. So the work done, which is equal to F times S, is going to be equal to mg times delta H. So this is what we call EP, which is the gravitational potential energy, which is given by the equation mg delta H. So in fact this is actually the change in gravitational potential energy, because when we move this object from there to there, its gravitational potential energy changed by an amount mg delta H. So here's an example of applying that. So an exercise weight of mass 50 kilograms is raised by a distance 1.5 meters vertically. So we have like a little exercise weight like this, and it's lifted up by a distance 1.5 meters, and it's then lowered by 1 meter. Calculate the change in gravitational potential energy for each step. So delta EP is equal to mg delta H. So we'll call this step 1, step A, and step B. So for A, delta EP is equal to 50 times 1.5 times G times 9.8, 9.81 we're using, 81 times delta H, which is 1.5, which gives us 50 times 9.81 times 1.5, 735.75. joules. And for B, delta EP is equal to, again, 50 times 9.81. And this time we'll call downwards negative, so that's negative 1.0, which is negative 490.5. So the total, this is part 1, and part 2, the total change in gravitational potential energy, delta EP total, is going to be equal to 735.75 plus negative 490.5, which is 735.75 plus 490.5 negative is 245.25. Joules. Okay, so here we see that we've had two changes in potential energy. One was positive and one was negative, so the total change was just the sum of the two changes. Note that we could have worked out the total change by just working out how far above it was. So this distance here is actually 0.5. So we could have just done delta EP total is equal to mg times 0.5. That would have been a quicker way to get to the final answer if we hadn't already been asked to do the first part. So no matter how we move it around, it's the final position relative to the original position that tells us the total change in gravitational potential energy. Okay, kinetic energy can be similarly derived using the work energy equivalence. So if we apply a force to an object, making it accelerate, then we can work out exactly how much kinetic energy it's been given by that work. So we can say here work is equal to force times displacement, and the force here is going to be the mass times the acceleration by Newton's second law. So F is equal to ma, but a is just the change in speed over the change in time, and we'll assume here that the object started at rest, so F is equal to, so we'll go m times v over t. This should be the change in v, but the change in v, if it started at 0, is just going to be the final speed. So we'll just write v there. The displacement during this time can be found using the equation v plus u over 2 times t. That's one of the kinematic equations, and we have a uniform acceleration here of a, and so we can use the kinematic equations, but u was 0, so s is just going to be equal to v over 2 times t. Now if we substitute these two into this original equation, we see that the work that we've done to accelerate this object is going to be equal to m times v over t, that's the force, times the displacement, which is v over 2 times t. And now we see that we can cancel this time, and we see that it's just 1/2 times m times v, which is v squared. So the amount of work that we've done on the object has led to the object accelerating, and that leads us to this equation, that the work that we've done is equal to 1/2 times the mass of the object times the final speed it reached squared. We call this type of energy kinetic energy, so we can write Ek is equal to 1/2 mv squared. And kinetic energy is always defined in comparison to what it would have had if it were standing still. So this assumption that U is 0 is always true when we're working with kinetic energy. So it's how much energy it has because of its motion at a particular speed, above 0. Okay. So kinetic energy too is related to the work done on the object. So here's an example. A stationary object of mass 5 kilograms is accelerated from rest to a speed of 12 meters per second. Question 1 asks us how much kinetic energy does it gain? We can just use the equation straight up. That's 1/2 mv squared, which is equal to 1/2 times 5 times 12 squared, which is equal to 0.5 times 5 times 12 squared is 360 joules. How much work was done by the net force on the object? The work done by the net force on the object is equal to the kinetic energy gained. So work is equal to delta Ek, which is equal to 360 joules. The work required to stop it would be equal to, so we want to stop it, we need to reduce Ek to 0, and this would require negative 360 joules of work. We'd have to apply a force in the opposite direction to the motion. Therefore, as it moves forwards while it's slowing down, we would be doing negative work on it. Alright, so to summarize this section, we do work by applying a force in the direction of motion of an object. The amount of work is the product of the component of the force in the direction of motion and the displacement of the object. Work is equivalent to the energy change of the object. If we do work against the motion of an object, the work done is negative and the object loses energy. The change in gravitational potential energy is the work done to change an object's height in a gravitational field. The kinetic energy of an object is defined as the work done to accelerate an object from rest to its current speed.